Math 3 Lesson Summary Video. Are you rational? This lesson is a solidify understanding task, which takes concepts developed previously and helps you formalize those ideas. The purpose of this lesson is to understand how rational functions reduce, as well as identify improper rational functions and write them in an equivalent form. The beginning of the lesson goes over definitions of rational number and rational function, which were discussed in the previous lesson. It has you to interpret definitions in your own words and solidify those ideas. On the second page, we move into actually talking about reducing fractions and going back and reviewing reducing fractions from your days in elementary school. If you think about reducing the fraction 24/30ths, the first job is to look for common factors. 24 is 8 times 3, and 8 is 4 times 2, and 4 is 2 times 2. So you get 2 times 2 times 2 times 3. And 30, when broken down into its prime factors, is 2 times 3 times 5. In order to reduce the fraction, you have to look for common factors, a factor that is on the top and on the bottom. So then you can divide those away. Whatever remains is the reduced fraction. It is no different with rational functions. As we learned in the polynomials unit, polynomials are just representations of numbers. And so the rules have to be the same. The first thing we did when they were just numbers was look for the prime factorization. We factored it. So our big rule for rational functions is always going to be to factor first. It's kind of a common theme as we deal with all of the operations for our rational functions and rational expressions. So first I want to factor. So here we can see the bottom has been factored for us, difference of squares. And on the top, if I were to factor, two numbers that multiply to equal -6, but add to equal -1 would be -3 and +2. Now, when I think about these common factors, or these factors in the numerator and these factors in the denominator, I do have a factor in common. Notice that there's an x plus 2 on the bottom and an x plus 2 on the top. So I can divide those factors. Please notice, we did not divide anything up here because you can't. When you have addition and subtraction holding your polynomials together, you can't just divide pieces of them. That's not how the division works. So we need to make sure that we have the prime factors, that we have factored it, because over here, what divided were the factors. All right, so you can't just randomly go around canceling and crossing things out. That's not how division works. You have to have factors, and they have to have factors that will actually divide each other out. And when you do, you're left with x minus 3 over x minus 2. You can try and reduce number 5 on your own. Factor, look for factors that will divide, and then keep whatever did not divide. Now, if we're given f of x is equal to x squared minus x minus 6, predict the vertical and horizontal asymptotes and find the intercept. So this is going back to reviewing what we were doing in the last lesson. If you recall, the vertical asymptotes are always determined by the denominator. So I want to figure out where's the denominator equal to 0. Well, this one we had already factored on the last problem. So I know it factors to be x plus 2 and x minus 2. So this is going to be equal to 0 where x is equal to -2 and x is equal to +2. So we should have two vertical asymptotes. Horizontal asymptotes. If you remember, the rule for that said for me to look at the degree. So first I need to look at the degree. I've got a degree of 2 on the top and a degree of 2 on the bottom. So they have the same degree. And we learned in the previous lesson that if they have the same degree, we need to divide the leading coefficients, take the ratio of those leading coefficients. So 1 divided by 1 gives me a horizontal asymptote of y equals 1. X-intercepts, we said, happen where the numerator is equal to 0. So let's see if we can figure out where the numerator is equal to 0. This factored to be x plus 2 and x minus 3. And that means that I'm going to have some x-intercepts at x equals -2 and x equals 3. All right. And then y-intercepts. We said our y-intercept is just what we get when we plug, or when we substitute 0 in for x. So 0, 0, -6. 0, -4. -6 over -4 is going to give us, let's see, our x-intercept we said was at -2, 0, and 3, 0. And our y-intercept is going to be at 0, 3/2. So that will give us our y-intercept. And then this is our x-intercepts. So that's all from our previous lesson. Now, we're going to use technology and look at the graph. So when we look at the graph, let's see if our predictions were correct. So looking here on my graph, I see I have a horizontal asymptote at y equals 1. Yep, that one worked. I have a vertical asymptote at 2. And wait a minute. I'm missing a vertical asymptote. That seems, now I have an x-intercept at 3, 0, but I don't have an x-intercept at -2, 0. And my y-intercept of 3/2, that looks okay. But why am I missing an x-intercept and a vertical asymptote? If we look at our factored forms and had paid attention before we just looked at all of our pieces of our graph, notice that this reduced. There was an x plus 2 on the top and an x plus 2 on the bottom, so they would divide one another out. So what we actually ended up graphing was x minus 3 over x minus 2. If we think about our rules that we learned in the previous lesson about all of our asymptotes, we would have a vertical asymptote at 2. We would have a horizontal asymptote at 1. We would have an x-intercept at 3 and a y-intercept at 3/2. And that is actually what we had. What occurs in the graph at x equals -2, if we actually look at -2, there's not an asymptote, but there's actually a physical hole in the graph. When a fraction reduces, it leaves a hole in the graph. Now, the reason it leaves a hole in the graph is because they divide out, they go away. We end up just graphing what is left. The problem is those would not have divided if x was equal to -2. I cannot divide by 0, ever. So these would not have divided and gone away if I had had x equal -2. So even though I don't have to graph a vertical asymptote and that x plus 2 is really having nothing to do with my function anymore, I still can't allow for x to equal -2 or it would have never reduced in the first place. And so I graph the graph, but then I have to make sure that there is a hole in the graph there. Next, we want to talk about proper and improper fractions. If you go back to your elementary school days and think about proper and improper fractions, remember proper fractions were of the form that the numerator was smaller than the denominator. An improper fraction was if the numerator was greater than the denominator. And with functions, it's not much different. It's just instead of actually talking about the value of the numbers themselves, we talk about the degree. So in a proper fraction, the degree of the numerator is less than the degree of the denominator. And in an improper fraction, the degree of the numerator is greater than the degree of the denominator. So it's still the same concept of bigger and smaller, but we're talking about degrees with polynomial degrees instead of just the value of the number. Just like when you were in elementary school, we also learned to take those improper fractions and write them as a mixed number. If you recall, the way that we would do that is you just had to do the division. So 2 goes into 7 3 times. 3 times 2 is 6. And then I have that remainder of 1. And in order to just write it as a mixed number, we take the remainder and we write it over the divisor. And so we would end up with 7/2 as an improper fraction would become 3½ as a mixed number. We can do the same thing with rational functions. Last module, we talked about polynomials, and we learned how to do long division with polynomials. So we actually did write mixed numbers last unit. So let's go back and give that a review real quick. So if we look at this particular improper rational function, I know it's improper because this has a degree of 2 and this has a degree of 1. 2 is bigger than 1, so this is an improper fraction. So I want to write it as a mixed number. So I need to remember how we did division with polynomials. So x squared divided by x is x. X times x is x squared. X times 2 is 2x. I subtract, and I get 3x. I carry down, and I start over. So x goes into 3x 3 times. 3 times x is 3x. 3 times 2 is 6. I'm going to subtract. And now I have 7 minus 6, which is 1. I have nothing left to carry down. X will not divide 1. And so I know this is my remainder. And just like with numbers, I'm going to remember to add the remainder on top of the divisor. So this is how we write a rational function instead of as an improper fraction, as a mixed number. Now, what's very interesting about thinking about these proper and improper fractions, and why is that even important, is that we did not investigate graphing in the last lesson when the numerator was greater than the denominator. And that makes it have a very interesting outcome. So if we wanted to graph this function, we're going to graph y equals x squared. Now this is its improper form. Let's take a look at it as a mixed number. We're going to write it as a mixed number. And then take a look at its graph. Let's take a look and see if there's some things that we notice are different. If we were graphing this, our rules tell us that our vertical asymptote is going to be at x equals -2, and that does in fact seem to be the case. I don't have any x-intercepts because this doesn't factor. It has imaginary roots, so I don't have any real roots. It doesn't have any x-intercepts. The y-intercept, when we plug in 0, we get 7/2, so it does look like I have 7/2. 3.5 is my y-intercept. But yesterday we determined if the degree on the top was equal to the degree on the bottom, our horizontal asymptote would be the ratio of the leading coefficients. If the top's degree was less than, if it was a proper fraction, if the top was less than the bottom, then its horizontal asymptote was always 0. But this is an improper fraction. And if we look at the graph, what happens with that horizontal asymptote is that in improper fractions, it's not horizontal. In an improper fraction, it's actually a slanted asymptote. And if we take a look at the mixed number, we find an even crazier association. If you take a look at our slanted asymptote, it has a y-intercept of 3 and a slope of 1. The equation of this line is x plus 3. What? So there's some great associations there. Now we know that there makes a difference if a rational function is a proper fraction or an improper fraction. Proper fractions have horizontal asymptotes. Improper fractions have slanted asymptotes. And anytime your rational function will reduce, that's going to leave a hole in your graph.